students, welcome to the session. Today in ray optics we are going to start refraction of light at a plane surface. Refraction of light at a plane surface. That is the topic we are going to discuss today. To know what is refraction of light, first we have to know about media, mainly optical medium. Optical medium. What is an optical medium? See this, optical. It's very easy. The medium which allows the light to pass through it is an optical medium. Any medium, that may be material medium or not. For example, water. Water allows the light to pass through it. It's a material medium. Vacuum. We all know light travels in vacuum also. So, whether it is material medium or not, if it allows the light to pass through it, is an optical medium. Generally, this media, two types. One, rarer medium. Second one, denser medium. How to decide whether it is rarer medium or denser medium? It's by comparing with the comparing speed of light in that medium. For example, if you take two media, for example, air and glass. We all know light travels faster in air than in glass, right? So, in that case, we consider air as rarer medium. Speed must be, greater. That means, in rarer medium, light travels faster. In denser medium, while comparing, denser medium, light speed will be lesser when compared with that one. Okay? Now, once you know about optical media, again this medium depending upon the speed. For example, if you take a particular material, if the light travels with the same speed in all directions, then that medium is called isotropic medium. Take one material, allow the light to travel in different directions. If the light travels with same speed in all directions, that is isotropic. For example, water. Water is isotropic. Glass is also isotropic, etc. But There are certain material media in which light travels with different speeds in different directions. Actually in our discussion we are not going to consider that type of material, one or two times we may consider, that's it. But most of the times we are going to consider isotropic medium only. Not only isotropic, it should be homogeneous also. In chemistry you might have studied about this homogeneous materials and all. It's very simple. Structure throughout the material, the structure should be same. The arrangement of atoms should be uniform. That is homogeneous. Okay, so just remember that. So mainly in isotropic. What is isotropic medium? The medium in which light travels with same speed in all directions. For example, if speed is differing, then it is anisotropic. Examples, I think you might have heard this. Calcite, tourmaline, etc. Okay, so these are all optical media only. Even in water glass, light propagates. Even in calcite, tourmaline, and other anisotropic media, light propagates. But what is the difference here? Light travels with same speed in all directions, but here in calcite, if you take in different directions, it will travel with different speeds. Okay, just remember that. So this is the introduction required to understand refraction, because refraction general meaning. Light, refraction takes place when light propagates or enters from one medium to another medium. For example, throughout this, only one medium is there, no refraction at all. What is refraction? We'll see. So that's why, to understand what is refraction, compulsory we have to take two different media. Okay, so let us start discussing about that refraction. So just try to remember where speed is more, where speed is less, speed of light. Okay, so mainly we are going to consider isotropic and homogeneous optical medium in this. Okay, look at that. Refraction at a plane surface, because refraction at spherical surface is also there, so that's why plane. Now you see this is a surface. That is one plane surface separating two media. Tell me, in one of the previous sessions already you might have considered this. Can you tell me what is that surface called? It is called interface. This is called interface. The surface which separates two media is interface. Let us consider this is rarer medium. This side say rarer medium. This side denser medium. This side. Okay. And you know, this is geometrical optics. In the last class, in one of the previous sessions, we discussed about what is angle of incidence and all. So to find angle of incidence, what is required? So compulsory a normal. Let us draw a normal to the surface. This is the normal drawn to that surface. plane surface. Normal. Try to remember, if the light travels along the normal like this, without any deviation, it propagates. So that's why light ray should be allowed to incident on the interface obliquely with certain angle. Say it's like this. This is the ray which is incidenting here. Okay, that is incident ray. Let us try to draw that straight. This one. Say PQ. Tell me what is PQ? Incident ray. Now tell me what is angle of incidence. We all know how to measure angle of incidence. This one. This is angle of incidence. Try to remember, if the light incident on interface, a part of light will be reflected, and a part of light enters into the other medium. We completed discussing about reflection. That's why we are not going to consider that part of light which will be reflected. Okay, just we have to consider the light that enters into the other medium. Tell me, when light, see actually if the medium is same, can you tell me the direction of light? You know, just now I said, if the medium is same, light travels in straight lines. This is, if the medium same, the light would have traveled in the same direction, right? But here, the light is entering into the other medium. We consider it as denser medium. Tell me where speed of light is more according to our discussion. We all know speed of light is greater in rarer medium when compared in this. That's why what happens, you know, try to remember. When light enters from rarer medium to denser medium, speed changes. Speed of light changes. Because of that change in speed, you know what happens here? The light ray bends. The light ray bends at the interface. Since speed is decreasing, it bends. This is the normal. Bends towards the normal. That means when light enters from one medium to another medium, observe this carefully. Observe that carefully. It is changing its direction. This is actually original direction. This is direction of incident ray. But here direction of this ray is changing. That change in direction of light ray when it enters from one medium to another medium is called refraction. Refraction. Here, tell me what is refraction? The phenomenon in which this happens, okay. Remember, this happens when light travels from rarer medium to denser medium or denser medium to rarer medium. Okay, I'll explain that also, that case also. First, let us consider. So, how to define refraction? When light enters from one medium to another medium, it is changing its direction, right? That's why the phenomenon of change in direction, of change in direction of light when it travels from one medium to another medium is called refraction. Clear? Even you can write like this. Bending of light. The bending of light at the interface is also called as, refraction. But as I said earlier in one of the previous classes, better learn the definitions according to NCERT. Okay. So what is that? The phenomenon of changing direction of light when it enters or travels from one medium to another. Okay, it's called refraction. Fine. Now tell me, what is PQ in the diagram? This diagram, what is PQ? PQ is incident ray. What is I? Angle of incidence. Now you know what is refraction. So what is QR? Refracted, right? If QR is refracted ray, the angle between refracted ray and normal is what? Angle of refraction. Angle of refraction. Now observe that carefully. Again, diagram. Actually, this is original direction of incident ray, but its direction is changed. That means the ray is deviated. That's why you can call it as this one. That is, tell me what is this angle? This is angle of deviation. How to define angle of deviation? It's very simple. It's angle, no? Angle between what? The angle between direction of incident ray, angle between direction of incident ray and refracted ray is called angle of deviation. So tell me what is angle of deviation. See, if this is I, this total angle is also I. That's why you get I minus R. See, this is I, the total angle is also I, but this one is R. That's why this value is I minus R. So angle of deviation is, but you should be careful. Angle of deviation is I minus R when light travels from rarer medium to denser medium. Okay? And one more point you have to remember. This point plays very important role while solving problems or numericals and all. When light enters from rarer medium to denser medium, the ray bends towards the normal. Why? Because speed decreases. Okay, and tell me, just try to recollect the physical quantities that remain same when light undergoes reflection. You know, when light undergoes reflection, speed remains same, wavelength remains same, frequency remains same, but energy changes. Here, remember, speed is changing. You know, speed of light changes because wavelength of light changes. Clear? Try to remember. So wavelength changes, speed changes, wavelength automatically, because wavelength change in wavelength only speed changes. But when light enters from, remember, when light enters from one medium to another medium, frequency doesn't change. Okay? Right. whether it enters from rarer to denser, any medium to another, any medium for that matter, frequency remains same. Okay, right. Energy anyhow changes. Energy changes because you know that a part of light will be reflected. Only a part of light. So, light enters into the other medium. Okay, only that part we consider. Next, second, this one, that is from rarer to denser. For example, this is an interface. This is an interface. Draw the normal. This is the normal drawn. Say this is rarer medium. This is denser medium. Light say entering from denser to rarer. This is angle of incidence. If the medium same, that would have traveled in that direction, but here medium is different. So now tell me, when it enters from denser to rarer, what happens to speed? Speed increases. That's why it bends away from the normal. Away from the normal. It's very simple. Why it bends? No, it should bend away from the normal. See, for example, you take just to understand that, let us consider here to here, to travel from here to here, say it is taking some one microsecond. In same 1 microsecond, it has to travel longer distance because speed is increasing, no? When speed increases, distance should increase. So only when it bends away from the normal, it can travel longer distance. That's why here you see, speed is decreasing. That's why it has to travel less distance in the same interval of time. For example, here to here 1 microsecond means here also you have to take the same time. So it has to travel less time. So when it bends towards the normal, then only it can travel lesser distance. That's why it's very simple. So this is PQ incident ray, QR refracted ray. Now observe this. See, if this is I, this is also I. But here this is refracted ray. That's why this one is angle of refraction. Now observe deviation. This is right, deviation. Can you tell me deviation here? Angle of deviation in this case. So here angle of deviation is equal to, which one is greater here? R. So R minus. So sometimes you can get this question for 1 mark. What is angle of deviation when light travels from rarer to denser or denser to rarer? So you should be very careful. This is I minus R, here it is R minus I, because this is R, this is I. So that's why it should be R minus I. Okay. So this is about refraction on some important points. Angle of deviation is important. Try to remember that. Okay. Once you know what is refraction, now observe the diagram. I'll retain the diagram. Let's erase this part. Let us erase this. Okay. While discussing about reflection, tell me what all the important topics we discussed. One, laws of reflection. Just try to recollect laws of reflection. Here, laws of refraction. First one, see, actually the scientist, namely Snell, experimentally obtained the laws of refraction. With repeated experiments, okay, Snell obtained two laws. One, it's very simple. What is PQ? Incident ray. QR, refracted ray. This one is normal. They should lie on the same plane at the point of incidence. It's like in that laws of reflection. Okay, they are also same, but there we consider reflected ray. Here we have to consider refracted. Okay, so tell me that incident ray, refracted ray, and normal. Light should lie on the same plane at the point of incidence. Okay. Second one is very, very important. Remember, ray optics 4 parts. No, one part is completed, still 4 more parts. Second part started. So in every other this one we are going to consider the second law, that is called Snell's law. Second one, Snell's law. This is also very, very important, exams point of view for 2 marks. Write laws of refraction, or simply you can get what is Snell's law. Okay, it is also very simple. See this. What is I? Angle of incidence. Can you tell me sine of angle of incidence? How to write sine of angle of incidence? Sine of angle of incidence. Similarly, how to write sine of angle of refraction? Sine R. This is sine of angle of incidence. This is sine of angle of refraction. Snell's law states that the ratio of these two, the ratio of sine of angle of incidence and sine of angle of refraction, is constant. But under certain conditions. This ratio is always constant. Constant means what? Some students, will not be knowing the meaning of constant. Constant means whatever may be the angle of incidence and corresponding angle of refraction, the value, for example, the value, whatever the value you are going to get, it should be same. The value what you are going to get here when you calculate this, it should be same for any angle of incidence. For example, angle of incidence say 30. Say this is something, whatever it may be. If you calculate those two, if you get 1.3, if angle of incidence is changed 40, 50, 60, whatever it may be, it should be 1.3 only. The value should not change. That is the meaning of constant, okay? But this remains constant under certain conditions. First condition, same color, wavelength of light should not change. Remember, for example, say PQ is red color, red. Though you change angle of incidence from 30 to 40, 40 to 50, the color should not change. When color changes, this value will change. So remember, so wavelength should remain same. Next, second condition, we considered rarer medium here, denser medium here. The pair should not change. For example, here it is air, say air. Here say glass. This pair should not change. Though you change angle of incidence, that means this is constant for a particular pair of media. For example, say angle of incidence 30. When angle of incidence is 30, if you consider these two media, when angle of incidence is changed from 30 to 40 by changing here, this medium, say for example, instead of glass, if you take water, this value will change. You are not going to get 1.3. Just I am mentioning one number. Don't think that you are going to get 1.3. Just that's it. You will get different value. Because whenever this pair changes, this value changes. That's why under two conditions, this ratio remains constant. That is called Snell's law. Tell me what are those two conditions? One, wavelength should remain same. That means this is constant for a particular wavelength and for a particular pair of medium. That's why while stating the Snell's law, you have to include those 2 points also. Tell me how to state this Snell's law. It's very simple. The ratio of sine of angle of incidence and sine of angle of refraction is constant for a particular wavelength and particular pair of media. Once again I will repeat. The ratio of sine of angle of incidence and sine of angle of refraction is constant. Tell me, for a particular wavelength and particular pair of media. Clear? It's very important. Tell me, see here, this is obliquely incident ray. For example, if this PQ is allowed to travel along the normal, what is angle of incidence? Tell me what is angle of incidence? Zero. See, if this PQ is traveling along the normal, that is called normal incidence. For normal incidence, what is I? 0. If I is 0, R must be 0. Right? So I is 0, R 0. Then sine 0. What is sine 0? We all know 0. It is undefined. 0 by 0 is undefined. That's why Snell's law is not valid. Try to remember, Snell's law is not valid for normal incidence. Sometimes you can get the question like this. What is the limitation? What is the limitation of Snell's law? Otherwise, you can get the question like this also. When Snell's law is not valid, limitation are not valid for normal incidence. Okay? So this is very important. Laws of refraction question is very, very important. So try to remember. My suggestion, try to remember this point. Wherever refraction is taking place, whether it is a plane surface or a curved surface, whatever it may be, if refraction is taking place, you can apply Snell's law there. Okay? But though you apply, Snell's law appears to be very simple, you should be very careful. I'll tell you. Okay? So this is about laws of refraction. Now, continuation. Once you know what is Snell's law, look at this constant. Okay, next topic related to this constant only. This constant is called refractive index. In Snell's law, this ratio is constant, no? This constant is called refractive index of the material of the medium. Okay, we'll see that. Okay, Snell's law. Tell me, what is Snell's law? It is sin I by sin R is equal to constant. What is this constant called? This constant is called refractive index. Refractive index. Remember, this refractive index is denoted with N. Okay, according to NCR it is N only, but in some books you may find even this letter also, mu. Okay. Now, how to define refractive index? Same definition, but especially while discussing about refractive index, you should be very careful. Okay, I forgot one point. Snell's law, I said directly, Snell's law is sin I by sin R is equal to constant, right? But don't worry, we are going to prove that. But in the next chapter, in wave optics, by applying Huygens principle, we can prove that sin I by sin R is equal to constant. That is there in your syllabus, so we are going to prove that. Even I is equal to R, angle of incidence in that reflection. Angle of incidence is equal to angle of reflection. That also we are going to prove. This also will be proved in the next chapter. Okay. For time being, just remember this. Now, let us consider this refractive index now. Okay. See here, while applying Snell's law, you should remember this point always. As long as you remember this Snell's law, you have to remember this point. See, here the light is entering from rarer medium to denser medium. Concentrate here. Say, I will consider this as medium 1. Say M1. Say this is M2, medium 2. Rarer medium to denser medium. That means medium 1 to medium 2 it is entering. Remember, you have to find out refractive index of this medium with respect to this. That means refractive index of medium 2, like this we write, medium 2 with respect to medium 1. So this constant is refractive index of which material medium? The material medium of this one, medium, that is denser medium. For example, if the light is entering from denser to rarer, for example, denser to rarer, you have to find out the refractive index of this medium with respect to this. I'll explain that also. Okay, so this is sin I by sin. Okay, so what is N21? Refractive index of medium 2 with respect to medium 1 is equal to sin I by sin R. This can be written as, this N21 can be written as N2 by N1, that is sin I by sin R. Now you have to remember this. What is N2? What is N2? N21, concentrate on my words. N21 is refractive index of medium 2 with respect to medium 1. N2 is absolute refractive index of medium 2. Similarly, N1 is absolute refractive index of medium 1. Is that clear? I considered here air, but you can consider any medium. Here I considered glass, you can consider water here. You can consider diamond, any isotropic optical medium you can consider, okay? I considered it. Remember, whenever you consider absolute refractive index of any material medium, with respect to, try to remember this, with respect to vacuum, free space or air. Okay? So absolute refractive index of, say for example, glass with respect to air, free space. Absolute refractive index of water with respect to free space, vacuum. Absolute refractive index of diamond with respect to. So remember, absolute means another medium should be free space or vacuum. Okay, if the second medium is not air or free space, then you can't call it as absolute refractive index. That is relative refractive index. For example, if light is here air, so that's why the refractive index of glass is absolute only. But instead of air, if water is there, then the refractive index of glass is called relative refractive index. We'll discuss that in detail. Okay? So what is N2? You know. Now, first let us discuss some important points related to this absolute refractive index. That is denoted with N. Okay. I said no, we are going to prove this Snell's law. While proving this, you are going to get this. So for timing, remember again, no other choice here. This is absolute refractive index. See this? N is absolute refractive index of a given material medium. C, you all know what is C? Speed of light in vacuum, free space. Air also you can write. C, speed of light in the given medium. I hope you all know C is the maximum value. Speed of light cannot be greater than this value in any medium. So it should be less than. That's why you see C is always greater than V. It may be equal. It may be equal to C. For example, if this is also air, here also air, here also air. For example, here vacuum, here air. So in vacuum and air, speed travels with same speed. That's why it can be C, but it cannot be greater than C. That is the reason why this N value, absolute refractive index, is always, remember this, is always greater than or equal to 1. It never be less than 1, remember. Okay, why? Because C is always greater than B. Okay, but if you consider air, it may be equal. C by C, you will get 1. Now, how to define this absolute refractive index? Like this only. The ratio of speed of light in vacuum and speed of light in a medium is called absolute refractive index of that medium. That means, for example, if glass is given, refractive index of glass. But again and again I am telling, while finding out absolute refractive index, one should be free space. One medium should be free space. That means with respect to vacuum only. Okay. Right. Next. Where I have to write? Okay. See this? C by V. I have to erase this. No other choice. Is that clear? Absolute refractive index C is the ratio of C and V. Sometimes in board exams, 1 mark question, how you can expect, can the absolute refractive index of material medium be less than 1? Absolute refractive index of material medium be less than 1? No. Your answer should be no. Absolute refractive index is always greater than or equal to 1. Okay. Now, let us consider that absolute refractive index once again. That is C by V. Now tell me, when light enters from one medium to another medium, the physical quantities that remain same, frequency. We all know V equals F lambda. F lambda. When light enters from air to glass, water to glass, diamond to glass, or glass to air, whatever it may be, frequency remains same, right? So, see, F nu, actually you have to write nu, as I said in one of the previous classes, nu lambda, but I will use because V is also there is a chance of getting confused. That's why I am using this F lambda. Lambda is wavelength of light in vacuum. This one medium. Okay, I'll write M here in the given medium. So F doesn't change. When light travels from one medium to another medium, frequency remains same, but wavelength changes. Okay, so F cancel. Therefore, N is equal to lambda by lambda medium. Okay, so this is refractive index in terms of speeds, this is in terms of this one. Now you have to remember, this is absolute refractive index. Now absolute refractive index is inversely proportional to wavelength of light in the given medium. Okay, this is in vacuum, no, it is constant, but if medium changes, this will change. That's why absolute refractive index is inversely proportional to wavelength. Okay, try to remember this also. This is about absolute refractive index, right? Next, once you know absolute refractive index, if the second medium is not, for example, I will take water here, then you can't call this, refractive index of this medium as absolute. It should be relative. Okay. N1 relative refractive index. Okay. Now let us consider that only. Tell me how to write refractive index of medium 2 with respect to medium 1. Right? This can be written as N2 by N1. Tell me what is N2? That is absolute refractive index of medium 2. Just now we finished that. Can you tell me how we can write N2? C by V2, because absolute refractive index is equal to C by V. Right? So medium 2, that's why V2. Next N1, C by V1. Therefore N21, and in the place of N2, C by V2, therefore okay, this is relative refractive index definition. How to define? The relative refractive index of medium 2 with respect to medium 1 can be defined as the ratio of speed of light in medium 1 to speed of light in medium 2. Relative refractive index of medium 2 with respect to medium 1 is defined as the ratio of speed of light in medium 1 and speed of light in medium 2. Now tell me, if light is entering from here to there, what is this? This is relative refractive index. Okay, I'll write that in words here first. Relative refractive index of medium 2 with respect to medium 1. Now this you know, relative refractive index of medium 1 with respect to medium 2. So that's why if 2-1 is V1 by V2, what you get here? V2 by V1. Right? If N21 is V1 by V2, N12, because N12 can be written as N1 by N2. This can be written as N1 by N2. Substitute these N1 and N2 values. You are going to get V2 by V1. Now, tell me the value about the refractive index, the relative refractive index. Tell me the value of relative refractive index. Yes. What is the value of absolute refractive index of material medium? It is always greater than or equal to 1. 1. Remember, absolute refractive index of vacuum is 1. For air also it is almost 1, but it is slightly greater than 1. Absolute refractive index of air 1.00029. So 1.0003 we can consider, okay, almost 1. But for any other medium other than those two, for glass, for water, for diamond, it should be greater than 1. Okay, but what about relative refractive index? Remember, for example, if N21 is less than 1, N12 100% greater than 1. I'll give you an example also. Okay, so if this is less than 1, it should be greater than 1. If it is greater than 1, it should be less than 1. That's why that relative refractive index is there, no? That relative refractive index, okay, it can be less than 1 also. Less than 1 or greater than 1. Okay, how? Let us discuss with the examples, okay? Example. See here, refractive index of glass with respect to water. Take the help of this and tell me what we can write here. Ng by Nw. See here, N21, we are going to get V1 by V2. That's why you will get dW by dG. If you refer the books, you will come to know that speed of light in water is greater. Okay, and glass. Okay, then therefore, if VW is greater than, what is this? This is relative refractive index of glass with respect to water. This next. Tell me. Okay. To get clarity, I'll take, I think, glass. Okay, diamond now. This is refractive index of, relative refractive index of glass with respect to diamond. So you are going to get V diamond B by Vg, right? According to this explanation. But tell me, where speed is more? In Vd is less than Vg, diamond. Diamond absolute refractive index is nearly 2.42. For normal glass, it is 1.5. That is absolute. But relative, it depends upon the second medium. You see here, this is also refractive index of glass. This is also refractive index of glass. But with respect to water here, with respect to diamond here. Now tell me, what if Vd is less than Vg? If this is less, we are going to get less than 1. So, relative refractive index may be greater than 1 or less than 1. So, this is about refractive index. Very important, refractive index. Okay. Finally, just observe that information we considered now. And sometimes you can get the question like this. Refractive index of a material medium depends on what factors? Tell me. Tell me, what is refractive index of air? 1.000. What is refractive index of glass, normal glass? 1.5. Refractive index of water, 4 by 3, 1.33. Refractive index of diamond is nearly 2.4. That means refractive index is different for different materials. So that's why it depends upon nature of the material. Nature of the material medium. Right. Second one. What is the relation between refractive index and wavelength? Just now, a few minutes back, we considered that relation. N is inversely proportional to wavelength. That means when wavelength changes, refractive index also changes. That's why it depends on wavelength. Color. While if different colors are allowed to enter into the same medium, refractive index change. So refractive index changes. So it depends on wavelength. It also depends on temperature. Remember, if temperature increases, refractive index decreases. If temperature of a material medium increases, refractive index decreases. So sometimes you can get this question also. On what factors refractive index of material medium depends. So nature of the material. I already given some examples. Say for example, if we take refractive index of air, refractive index of water, this is refractive index of normal gas. Okay, so like this. As material change, this one also will change. But you see, that absolute refractive index never be less than 1. It is always greater than 1. Depends on temperature also. Clear? So this is about refractive index. It has no units. Remember, refractive index has no units and dimension because it is the ratio of same. Refractive index is sin I by sin R, right? Or C by V. There are different, remember, to calculate refractive index, there are different formulae. So, depending upon the given data in the problems or MCQs, you have to select the correct one. N is equal to sin I by sin R. Today only we use 3 to 4. N is equal to sin I by sin R. N is equal to C by V. N is equal to lambda by lambda medium. N to 1, if it comes to N to 1, relative V1 by V2. So, depending upon the given data, you have to select the correct one. But if you take any formula, C by V, C is also speed, V is also speed. So, units get cancelled. I by I, theta, units get cancelled. Okay? So, lambda, wavelength, same units cancel. That's why refractive index has no units and dimensions. Okay? So once you know what is refraction, laws of refraction, and mainly Snell's law, now this refraction, this refraction of light is a common experience in our daily life. For example, take one toothbrush or anything, one stick, just try to immerse that in water, then observe that carefully. Whenever it is immersed in water or any other liquid, what do you feel? We feel that it looks like bending, right? Looks like bending. That is because of refraction only. It's common experience. But in your syllabus, by taking this refraction into consideration, we are going to discuss about some concepts. I'll mention the concepts and we'll discuss those concepts in the next session. 1. take two parallel sides, okay, two parallel sides, and allow the light to pass through those parallel sides. So what happens? And second one, this is common experience. If you look at the bottom of a swimming pool, we always feel that it is closed. It appears to be closed. It appears to be shifted than the normal depth. That is also because of refraction. And the most important one, exams point of view for 1 or 2 marks, not more than that, atmospheric refraction. Because of atmospheric refraction, what happens? And some other concepts also there. We'll discuss those concepts in the next session, okay?